Hi, this is Dr. Remenacker. I want to welcome you to the first of what I plan to be two videos that deal with asymptotes and graphing rational functions, and then the second video will deal with exponential and logarithmic functions. All right, so if we're going to be graphing rational functions, need to remind ourselves what is a rational function. Well, a rational function is a function, it's basically a fraction where the numerator and the denominator are some form of a polynomial. Now, a reminder, polynomials can look like 3, that's a polynomial, 3x plus 4, 2x squared plus 7x minus 9. It can be a combination of constants and variables, x in this case, to different um, degrees, okay, to different exponential powers. Another very important thing to keep in mind is that the denominator, whatever g of x is, cannot be 0. And the domain is going to be all of the x values where g of x is not 0. We'll quantify that here in a little bit. In fact, we'll quantify it here in the example we're going to take a look at now. Okay, so what the case is we're going to be looking for vertical asymptotes. Now, vertical asymptotes occur where the denominator of a simplified rational function is 0. Keyword here, simplified. You can have um, various factors that can cancel. Those are called removable singularities. But let's take a look at a situation here where we have a polynomial in a numerator and a polynomial in the denominator. And what I'm first going to do is I'm going to look at factoring this. This will factor, the numerator is a difference of two squares. This will factor into x plus 3 times x minus 3. The denominator will factor into x plus 5 and x minus 4. Okay, so there you go. That's the way this thing factors. Once you have it factored, the vertical asymptotes, which I will abbreviate as VA, occur where the denominator equals 0. Okay, so this means that we want to know where does x plus 5 times x minus 4 equal 0. These are going to be values of x for which our rational function is undefined. Undefined because you're getting a 0 in the denominator. Well, the values that we're going to be looking at are x equals a negative 5 or x equals 4. So we wind up with vertical asymptotes at x equal to a negative 5 and x equal to 4. When we go to graph this, okay, a quick way to start to set up some of the conditions for the graph are to come over here to negative 5, move to the right to positive 4, and set up vertical asymptotes. Remember, vertical asymptotes are lines that the graph is typically not allowed to cross. Okay, I always think of them as being something like barbed wire. You definitely don't want to mess with trying to climb over barbed wire. Okay, so x equals negative 5 and x equals 4 is going to give us some asymptotes. Not quite sure exactly what's going to happen, but the function's going to do something or other like this. I don't know exactly what it is. We'll deal with getting those pieces filled in here in a little bit. In general, vertical asymptotes occur if any of the following situations exist. If you have a limit of f of x, okay, and that limit is going to infinity as you come at some number from the negative side, or the limit is going to negative infinity as you approach some number from the left side. That's going to be an asymptote. It can also be the situation that if you approach a value from the right-hand side, it goes to infinity or it goes to negative infinity. Okay, so that's more of a mathematical definition of what's going on. Let's take a look at some situations here where we're actually going to identify our vertical asymptotes. As a first example here, let's take a look at 2x plus 5 over x minus 7 times x minus 4 squared. The first thing I want to do is to take the denominator and factor it as much as I can. Once it's factored, it's a little bit easier to see exactly what's going on. The x squared minus 4 will factor into x minus 2 and x plus 2. This then gives us asymptotes, 3 of them, at x equals 7, x equals 2, and x equals negative 2. Okay, so we've got those three situations or locations where we can wind up with vertical asymptotes. A good policy or practice is to first go to your graph. Here it is to the right. Over at 7, 2, and at negative 2, the first thing I'm going to do is to sketch in my vertical asymptotes, just like we did before. Okay, and this provides some direction as to places where the asymptote can or where the graph can or cannot occur. Let's take a look at this second situation here. In this situation, this will factor to give us x times x minus 3 over, hey look, in the denominator we can factor out an x. We're going to have x squared minus 4. This will factor a little bit further. It gives us okay, this can factor a little further. In the numerator, we're going to have x times x minus 3 divided by, we're going to have x times this x squared minus 4 in the denominator. However, as you're probably already thinking, hey, that denominator will factor even further. And this will give us x times x minus 2 times x plus 2. Now, this takes us back to something that I mentioned very early in the video. I mentioned it, the simplified version of the rational function has zeros in the denominator. This rational function that we have right here is not simplified. You can cancel out an x. Now it's simplified, and in this case, the vertical asymptotes occur, as always, where the denominator is 0, and that's going to be where x equals 2 or negative 2. Notice the x equals 0 in this case canceled out. Okay, let's go on a little bit further. You can have vertical asymptotes, which is like what we sketched on the upper right corner here. You can also have horizontal asymptotes. Now with a horizontal asymptote, it basically is a situation with the behavior of the function as x goes to infinity or negative infinity. So for example, if I have a graph and this thing is leveling it out, I'm just going to put a 2 here. And it levels out over time that it's leveling out at 2. You have here a horizontal asymptote at y equals 2. Okay, so you can have horizontal asymptotes like that. The way that you get a horizontal asymptote is by applying the limit as x goes to infinity or as x goes to negative infinity. So to get a horizontal asymptote here, if they exist, they don't have to exist. What we're going to do is we're going to do this limit as x goes to infinity of our x squared minus 4 over our x squared minus 2x minus 15. Now, you need to pull up some of the properties of limits at infinity that we worked on earlier. Okay, recall that if the numerator and the denominator have the same degree, in other words, the same power of exponent, all you do is you take the coefficients off of those two, in this case, one in the numerator, one in the denominator. We have a horizontal asymptote as x, actually as y, approaches 1. X is going to infinity. You also want to consider what's the limit as x approaches negative infinity for this function. It's going to be this x squared minus 4 over the x squared minus 2x minus 15. Once again, just as previously, we've got a tie on our exponents, okay? And we're going to go ahead and pull these coefficients off of here, and it's going to give us 1 over 1. If there's a tie, okay, sometimes people say, well, what would happen if I have, and we'll keep this kind of simple, the limit as x goes to negative infinity of x cubed over x cubed. Here we have a tie. And if you plug large negative numbers into the x cubed in the numerator, you're going to get a negative value back. However, you're also going to get a negative value back in the denominator. So that's going to give you a negative over a negative, which is still going to give you a positive. You do need to be mindful of what's going on with your positives and your negatives. For example, suppose this is 2 and this is now a negative 7. Well, because there's a tie, okay, because there's a tie, we're going to be dealing with our coefficients. And you may say, well, yeah, there's the 2 and the negative 7, but when I plug the negative infinity or large negative numbers into x cubed, what's that going to do now? Well, you're going to get a negative value in the numerator, large negative number. However, if you plug negative 10,000 into the denominator and cube it, you're still going to get a negative. This is still going to go positive on us. And just as we talked about earlier, you're still just running with the coefficients off of the two different polynomials. Okay, so to get horizontal asymptotes, you want to consider the limit as x goes to infinity or negative infinity. Okay. In the situation here, you're asked to locate the horizontal asymptotes for this. Well, I'm just going to do the limit as x approaches infinity of this 5x plus 7 over x. Notice the highest degree in the numerator is a 1. The highest degree in the denominator is a 1. It's a tie. So we're going to wind up with the limit evaluating to be 5 over 1, which is 5. This means that we have a horizontal asymptote, not at x equals, but at y equals 5. Well, why isn't it x equals? Well, it's not too hard to see here. X is going to infinity. And as x goes to infinity, it's the y value that's going to go to 5. All right, so we've taken a look at vertical asymptotes, the type of asymptotes you probably learned about first. We then took a look at horizontal asymptotes, which are dependent on a limit as x goes to infinity or negative infinity. We're going to take a look at one that you may or you may not have seen in an earlier math class. This type of asymptote is referred to as either a slant asymptote or an oblique asymptote. Either name is fine, two different names, same thing. These occur where the exponent or the degree in the numerator is exactly 1 degree higher than the degree of the denominator. Let's take a look at an example of this. Here we have at the upper left corner x squared minus 9 over x plus 2. Notice that the exponent in the numerator is a 2. The exponent in the denominator is a 1. So we do have a situation where the exponent in the numerator is exactly 1 degree higher than the exponent in the denominator. To compute where the slant asymptote occurs, we've got to go back to division, long division. Uh-oh, this may take you back a few years. Remember back in maybe freshman algebra and you're thinking, why do I have to learn how to divide polynomials? This is dumb. I'm never going to need it. Well, you need it. So what winds up happening here is we're going to have the x plus 2 divided into, now I could write x squared minus 9. However, that's ignoring the fact that this polynomial really looks like x squared plus 0 times x minus 9. So that's truly what the numerator looks like when it's written out in its full glory. Okay? Then to do this division, what we want to do is we want to focus on this term right here. And the question is, what do I multiply the term there to make it look exactly like x squared? Well, to make it look exactly like x squared, I'm going to multiply by x. Then I'm going to take this x and multiply it times each of those. The x times the x is going to give me x squared. The x times the 2 is going to be plus 2x. Okay, this is where people sometimes get a little confused. Let's go back to about 4th or 5th grade math where you learned long division. Let's say we're dividing 3 into 47. And the first thing you want to do is ask yourself, how many times will 3 go into 4? Well, it goes one time. You take the 1 times the 3. That gives you the 3. You draw the line. Now, you don't add the 4 and the 3 together. You subtract. Oh, yeah. Going back over to the green here on the right-hand side, same deal. You subtract. But be careful. You don't just subtract the x squared. You subtract that whole polynomial that we have written down there. So what we're going to have is x squared minus x squared. Those will cancel out. Here's where you got to be careful. We have 0x. It isn't plus 2x, but it's actually going to be a minus x because, oh yeah, that's going to be a minus 2x there. So what you're going to have is 0x minus 2x. So we're going to wind up with a minus 2x. Notice there's nothing in this place. So I'm just going to bring down the minus 9. All right, at the next step in the division, I want to make this leading term here look exactly like that. Well, I accomplish that by multiplying by a negative 2. Because the negative 2, this whole deal, times the x will give me a minus 2x. When I multiply that by the negative 2, I also need to multiply the plus 2 by a negative 2. In other words, distribute. This is going to give me a minus 2x minus 4. As in the previous step, I'm going to subtract that. This will now give me my minus 2x here, and we're going to have minus a minus 2x, which is going to be a minus 2x plus 2x. These cancel out. Moving over to the next place, I have a minus 9, and then I'm going to have a minus 4. Minus a minus 4 is going to be plus 4, so I have a minus 9 plus 4, which is going to give me a minus 5. Okay, so at this point, I'm done. I don't worry about the remainder down here. I don't worry about that when I'm looking for the slant asymptote. But what I do focus on is this. My slant asymptote is going to be the equation y is equal to x minus 2. When I go to graph this function, okay, I'm going to have some other asymptotes, but I'm also going to have a situation here where I have a slant asymptote at x minus 2. So what I need to do is I need to graph the line y equals x minus 2, which means I need to come down 2. It's going to be at a 45-degree angle since the slope is 1, and I'm just going to put in a line like this. And I'm definitely going to label this as y is equal to x minus 2, so I know what that slant asymptote actually looks like. Going back to the original function in the upper left-hand corner, I also want to consider, does this have any vertical asymptotes? Well, recall, vertical asymptotes occur where the denominator is 0. The denominator is 0 at x equals a negative 2. So if I come x equals a negative 2 there, I can plug in and put my vertical asymptote there at x equals negative 2. Notice I have labeled both asymptotes. Now the question is, where's the graph? Okay, well, one way to deal with this is to ask ourselves, where does it intersect the x-axis? Okay, it intersects the x-axis where the numerator equals 0. So the x-intercepts okay, and remember to be an x-intercept, I'm looking back over here at this blue graph, to be an x-intercept, that means the y value has to be 0. Well, for my function to be 0, if I want my y value 0, my x minus 3 times my x plus 3, I'm just factoring, over this x plus 2 has to be 0. A fraction can only equal 0 if the numerator is 0. Well, the numerator equals 0 only occurs where x is equal to negative 3 or positive 3. Okay, well, what's that get for me? On my graph, if I come over to negative 3, I'm intersecting right there. I have an x-intercept. Now, on this slant asymptote, y is equal to x minus 2. If I want to know where does this line intersect the x-axis, I want my y value to be 0, which means my x value is going to be 2. So this graph intersects the x-axis right here at 2, 0. Now that's useful information because remember my other x-intercept is at a positive 3. Well, that's over here. So when I go to graph my function is actually going to be intersecting the x-axis at these two locations in green. Well, the only way that can happen is if the graph goes like this. And remember, the graph's going to get closer to these asymptotes and like that. And there's the graph. It's just that simple. Okay. So one of the things we want to consider is where does the graph intersect the x-axis? That means where does y equal 0? We also want to consider where does it intersect the y-axis? Oh, yeah, where would it intersect the y-axis, the y-intercept? Well, remember, the y-intercept means it's hitting the y-axis, but that just means x equals 0. If x is 0, all I do is I go back to my original function, and in place of x, I plug in 0. So I'm going to get 0 minus 9 over 0 plus 2. That allows me to then come onto this graph and say, you know what, 3, 4, 5. This location right here is when x is 0 and y is a negative 4.5. Or you could put 9/2, whichever you want. Okay. This allows you to locate your x-intercepts, where does it intersect the x-axis? Your y-intercepts, where does it intercept the y-axis? And get some additional points to help you sketch the graph. Okay, let's take a look at this situation here. Let's try to rough out a sketch of this, just looking at the intercepts and just looking at the asymptotes. So I'm going to come over here to the right-hand side and put a fairly good sized graph down. There we go. Okay, first thing I'm going to do is I want my x-intercepts. Now, remember, x-intercepts mean that y is 0. The only way you can be on the x-axis is if y is 0. So for the x-intercepts, that means I want my equation, this x times the x minus 2 times the x plus 7 over this x plus 1 times x minus 4 to equal 0. As we discussed earlier, the only way a fraction can be 0 is if the numerator is 0. Okay, the numerator equals 0 occurs if x is 0. See it right here, x is 0. The numerator equals 0 occurs right here if x is 2. The numerator right here equals 0 if x is negative 7. So this gives us 3 locations where we're intersecting the x-axis. Those 3 locations, I'm going to go ahead and put them on my graph, are at 0. They're going to be over here at 2. And they're going to be to the left here, 2, 3, 4, 5, 6, 7. Negative 7. So I have those 3 locations for x-intercepts. The next thing I want to look at is where are my y-intercepts? Well, the y-intercepts mean, let's see, if I'm on the y-axis, that means x equals 0. Okay. X equals 0 means I'm just going to substitute in 0 into my original function. So that's going to give me y is equal to 0 times 0 minus 2 times 0 plus 7 over this 0 plus 1. See it? I'm just plugging in 0 for x. And then 0 minus 4. This is going to give me 0 times negative 2 times 7 over 1 times negative 4. I don't have to go too far here because in a numerator, you know what? I've got a 0 right there, which means the y value is going to be 0. If, however, that wasn't there, I could wind up with a negative 14 over a negative 4, which would simplify to be 7/2. So it could be that the y-intercept is at 7/2, which would be somewhere up here, 3.5. But, well, I didn't want to do that. But what I want to do here in this case is to also include this factor of 0 in the numerator, which is going to give me 0 in the numerator over negative 4, which is just 0. Oh, wow. This is telling me that when I draw this graph, my y-intercept is going to be the same location as one of my x-intercepts. It's going to be this right here. When x is 0, y is 0. Okay, so I have my 3 locations here where it intersects the x-axis. The next thing we want to take a look at is where are the vertical asymptotes? The vertical asymptotes occur where the denominator is 0. So the next thing I'm going to do here is I'm going to take a look at the vertical asymptotes. These occur where the denominator equals 0. Well, just looking at that real quick, like it's going to be at x equals -1 or 4. So I'm going to the -1 came from this x plus 1. The 4 came from the x minus 4. So I'm going to put these two locations on the graph. X equals -1 is going to go right here in green. And then I'm going to come over to x equals 4. And that's going to go right here in green. Okay, so we have our x-intercepts, we have our y-intercepts. We have our vertical asymptote. Next thing to ask ourselves is, does this have a horizontal asymptote? Well, I'm going to just kind of sketch out what this function looks like. And remember, I'm going to do the limit. And I'm just going to do as x goes to infinity because we're going to see something here. If I multiply out the numerator, okay, the function is jotted down at the top left corner. Notice the lead term in the numerator is going to be an x cubed. The lead term in the denominator is going to be an x squared. This should look familiar to you from earlier work with limits. In that work, if you were doing a limit as x goes to infinity, and the higher power of x is in the numerator, well, that just tells you that this equals infinity. So what this says is that our horizontal asymptote occurs at infinity, which doesn't exist. Okay, you can never get to infinity. This brings us to the third type of slant asymptote. Uh-oh. With a slant asymptote, oh no. The slant asymptote only occurs where the numerator is 1 degree higher than the denominator. Take a look up here at the horizontals. That's the situation we have here. Sure enough, we're going to have an x cubed over an x squared. So what I'm going to need to do here is I'm going to multiply out my function. So what I'm going to have is my y is equal to x times, and I'm going to do this just one step at a time so you can see what's going on. In the numerator, I have x minus 2 times x plus 7, which is going to give me x squared plus 5x minus 14. And if you're not sure of that, go ahead and FOIL it out. In the denominator, I have x plus 1 times x minus 4. That'll give me x squared minus 3x minus 4. X squared minus 3x minus 4. Distributing the x in the numerator is going to give me an x cubed plus 5x squared minus 14x over this x squared minus 3x minus 4. Okay, so when I multiply this all out, great. You can see that we definitely are looking at a situation where we're going to have a slant asymptote. All right, so how do we handle this? Well, I'm just going to take and do the division. I have an x squared minus 3x minus 4 divided into x cubed plus 5x squared minus 14x. And remember, this is really plus 0. First step in this, what do I multiply this lead term here by to make it look exactly like x cubed? Well, I just multiply by x. I'm going to put that in this x column. So that'll give me x cubed minus 3x squared minus 4x. Okay, so I've got that. Now, I come back and I subtract this x cubed minus 3x squared minus 4x. That means I'm going to distribute a negative over everything. My x cubes cancel. I'm going to have 5x squared minus a minus 3x. Oh, that's going to be plus 3x squared, which is going to give me 8x squared. I have a minus 14x minus a minus 4x, so that gives me a minus 10x. And I'm going to bring down this plus 0 just to be on the safe side. The next thing I want to do here is I want to know what number do I put here so that when I multiply it times this, it'll look exactly like this 8x squared. Well, I'm going to multiply by a plus 8. Then I'm going to take that plus 8 and I'm going to distribute it over this whole deal, which is going to give us 8x squared minus 24x minus 32. Okay, then just like in the previous step, I'm going to subtract it. And I'm going to distribute that negative over each of the terms. And that'll give me an 8x squared minus 8x squared. Those cancel. I'm going to have a minus 10x minus a minus. Oh, that's going to give me a 14x. And then I'm going to have 0 minus a minus, which is going to be plus 32. Well, at this step, the question is, can I put anything here, like a coefficient or something, to multiply x squared by to make it look exactly like x? Well, no, I'm done. Interesting. So I do have a slant asymptote. And my slant asymptote occurs at y equals x plus 8. Aha. The slope is 1. It intersects the y-axis at 8. So I'm going to come up 8. 1, 2, 3, 4, 5, 6, 7, 8. Because the slope is 1, it's going to be a kind of a 45-degree angle here. Okay, so we're going to have this, and this is at y equals x plus 8. This is at x is equal to 4, and this is at x is equal to negative 1. So I know where each of my boundaries are. I don't have to guess where they are. I know right where they are. And now comes the fun part. How on earth do I go about graphing something like this? Well, there are actually kind of a couple easy maneuvers here. First thing I want to do is over in this leftmost area, okay, I want to figure out where's the graph. To do that, what I'm going to do is I'm going to pick some x value. Now, if I pick something, I could pick something way over here, like negative 10 or something like that, but that looks kind of ugly to be putting in there. Okay, so I'm not going to pick x equals negative 10. I'll pick something simple like maybe x equals negative 2. And I'm going to plug that into my function. Well, L of negative 2 is going to be a negative 2 times negative 2 minus 2 and negative 2 plus 7. See, I'm just plugging in negative 2 in for x everywhere, over minus 2 plus 1 times negative 2 minus 4. Okay, so let's clean this up. This gives me L of negative 2 is going to be, let's see, it's going to be a negative 2 times a minus 4 times 5 over. This is going to be a negative 1 minus 6. Cleaning this up a little further, doing all this multiplying stuff. Negative 2 times negative 4 is going to be 8 times 5 is going to be 40 over 6. So that's 20 over 3. Okay, 20 over 3 is going to be a y value that's pretty big. That's going to be like almost 7. So at negative 2, my y value is going to be up here around 7. Oh, well, that's going to be something like this. So on this leftmost portion, it looks like my graph's going to go something like this. Okay, on the center portion of the graph, the center portion being this area right in here, I just want to pick some point that's easy to work with. And actually, this isn't horrible to work with here because I already have my two x-intercepts. With these two x-intercepts, the graph is either going to go like this, which would be kind of strange because it's crossing the slant asymptote, or the graph is going to come along this asymptote, go up through here, come back down, and go down that way. I know that's not the world's greatest graph, but it'll kind of give us an idea. Now, in the rightmost section, remember this is going to be things like x equals 5 and 6 and stuff like that. So I'm going to come over here to something like 6. And the question is, how's the graph behaving in this panel here? Well, what I'm going to do is I'm going to evaluate the function at 6. When I plug 6 in, I'm going to have 6 times 6 minus 2 is 4. Then 6 plus 7 is going to be 13 over, in the denominator, I'm going to have 6 plus 1 is 7 times the 6 minus 4 is 2. So what this is going to give me then is, let's see, the 4 times the 13 is going to be 52 times 6. 52 times 6 looks like about 312 over 14. In other words, this y value is going to be humongous. So what's going to wind up happening is my y value is going to put me up in this area. So there's the third portion of this graph. Okay. These take a little bit of practice. We're going to do some more of these or some more graphing in the next video. But for now, I'm going to call it quits with this particular video.